All right, class, I am going to deliver one more lecture, and hopefully by Saturday this pink eye will be completely gone, and I will be able to be back with you in class on Monday in person. So let's just keep our fingers crossed and hope that the antibiotics do their job. So we're going to be talking about one more mechanism where skeletal muscle kind of takes the control of blood flow. And this is the last conversation we're having about blood flow regulation in skeletal muscle. And this one's really important because much like the Golgi tendon and other reflexes in the muscle, scientists believe that we also have a pressor reflex that is activated with afferent neurons. And if you don't know what afferent means, that means neurons, like this picture I have here, leaving the muscle and going back up the central nervous system to the brain. So afferent neurons or afferent signaling is basically telling the brain to make small little changes that can happen through the rest of the systemic physiology. So when it comes to the pressor reflex, scientists believe that this reflex is activated during contraction, and this activation overrides central command. And that's why I had you guys take a test on central command. And there's a couple of different elements that play a role in regulating this process, just like we've talked about with every single mechanism. It's not just one particular thing, and there's several mechanisms at play here. They believe that lactate, ATP, high levels of hydrogen, growth factors. We've talked about a growth factor in our last lecture when we talked about VEGF, and even cytokines play a role in activating these afferent neurons that will take over control of blood flow. So it basically shuts down central command and it takes over full control of microvascular dynamics because of skeletal muscle contraction. So this is basically a snapshot of what the pressor reflex is, and it's basically during exercise we have a physiological response that helps regulate blood pressure. We've talked about that a lot, right? And increase the demands of blood delivery and oxygen delivery during physical activity. And so what we've talked about for the most part, and you guys have drawn pictures on this, is this central command, right? In central command, we know that if there's an increase in heart rate and there's an increase in blood pressure, well, we have these baroreceptors, and we didn't really talk much about chemoreceptors, so I'm just going to stick it with baroreceptors here. And the baroreceptors will notice that there is an increase in blood pressure, and you can see these neurons right here. They're going to send a message to central command, and central command will determine what to do with heart rate and what to do with blood pressure. And the baroreceptors obviously want to limit heart rate, right? So when there's an increase in blood pressure, they'll tell central command, hey, let's reduce heart rate. And if you follow these lines, let's reduce the sympathetic nervous system and vasodilation, right? And let's get blood pressure to kind of go back to its normal resting level. So we know that the pressor reflex comes into play as a means of maintaining a healthy blood pressure during oxygen. And I have this little arrow here because this is a reflex that stems from the skeletal muscle. And you can see here it's exercise pressor reflex. You can see here that there's two afferent neurons that will basically travel back up and communicate with the central nervous system. And once it gets to the central nervous system, central command will determine what to do. And of course, during exercise, we will want to continue to increase cardiac output, continue to increase heart rate. We will want to basically override the baroreceptors and say, okay, baroreceptors, it's okay to have elevated blood pressure right now because we're exercising. And then the brain will take all of this into consideration. It will cause vasodilation to help increase pressure. But then again, we know locally we will get an increase in blood flow and vasodilation by things that are coming from the skeletal muscle. We spent a lot of time talking about that. So I just want to kind of go over this first section as a central review, okay? And that's why I'm going to do this one online. And when we get in person, I will finish the rest of this talking about how the pressor reflex kind of overpowers central command. And this is, we've already talked about this. You've already drawn it. I'm going to go into a little more detail on this just to give you a better idea of some of the mechanisms involved in it. But if you just kind of look at this picture here, you already know this. You've already understand this. We've already kind of talked about this. So if we're talking specifically about what the baroreceptors do, well, these are special sensors, right? And they're located in the carotid arteries and in the aorta. So if you come back here, you see here, here's the aortic arch, and there's baroreceptors here. And then when we get to the carotid arteries up by our neck, we have them there. So we have these kind of pressure sensors at several places within the body. And one of the things they're doing is constantly monitoring changes in blood pressure. And just like that analogy I had given you a couple weeks ago when you're driving in Chicago traffic, it's this kind of fine dance between acceleration and brake and acceleration. And that's what keeps things moving. So we never have full constriction. We never have full dilation. It's kind of in the middle there, right? So this is monitoring, and especially it becomes more heightened during exercise. And basically what happens with the baroreceptors is they will continuously monitor, and then they will immediately respond, and they will give feedback to what is occurring to the brain, to the central command, right? So if we go back to this, we see that these things are monitoring changes in blood pressure. They're sending a message to central command, and then central command is going to do some type of feedback, which is going to be accelerate or decelerate heart rate. So again, depending on the situation, depending on whether we're exercising, depending on whether we're at rest, depending on whether we're walking up a flight of stairs, this very important sensor is going to communicate with central command, and it's going to make adjustments based upon the activity, right? The intensity of the activity. And generally, the baroreceptors, what their primary objective is to reduce cardiac output or heart rate, right? It wants to bring things back to homeostasis, or it wants to establish a new set point, right? So if we can begin to exercise and blood pressure rises, right, and then it plateaus, part of the job of the baroreceptor is to make sure it keeps the brain informed of the pressure that needs to be maintained during exercise or during an activity, right? So now how this all works is here, this is just kind of a reiteration. Baroreceptors, again, they're specialized sensors. They're constantly monitoring, right? So here's the baroreceptors right here. We have one on the aortic arch. We have them on the carotid arteries, right? And as you exercise, your muscles are going to increase activity, right? And they need more blood flow, which leads to an increase in blood pressure, right? The baroreceptors kind of play a role in that, right? So they're going to sense changes in pressure. They're going to send that message to the brain, to central command. The brain is going to analyze it, and then it's going to determine what the next step is, right? Is it going to increase heart rate or decrease heart rate? Is the brain also going to increase sympathetic nervous system drive, right? And cause vasodilation, right? And that's generally what tends to happen during exercise. And again, the central command ultimately determines what it's going to do to deliver sufficient oxygen and sufficient nutrients to those contracting muscles, which are down here. And just really quickly, you can see here that I just put some arrows here just to kind of help you out with this picture because it's a little bit convoluted and there's a lot of stuff happening. So again, this is just saying baroreceptors communicating with central command. Central command is going to induce some sort of reaction, right? And we will talk about the parasympathetic vagal nerve as well. We will talk about how this is kind of reduced, which will allow the brain to increase heart rate and cardiac output, right? So I just have those arrows there. They're also on the next slide as well. So here's how this all kind of works now. And I'm just kind of introducing afferent and efferent signaling, just in case you haven't heard it in a while, you don't remember it. So the cardiovascular control center, the signals from the baroreceptors are sent afferently, right? And the way I think of afferently is away. Things are moving away. So if I have a signal here and my afferent message is occurring, it's being sent away from the organ that has sensed it, and it's moving to a new organ, which in this case is the central command system. And then this afferent signaling, this movement away, leads to a central response in the brain, and then the brain is going to send an efferent signal an efferent signal to another organ. Another way to think about this is, my mouse is so sensitive. Another way to think about this is afferent signals come from the peripheral nervous system to the central nervous system, right? And efferent signals, they move from the central nervous system to the peripheral nervous system. So that's another way to kind of look at this, okay? And so when the baroreceptors receive information on changes in blood pressure, they send afferent signals to the central command. Central command processes it, and they send efferent signals back to the periphery, which in this case is going to be increasing the heart rate and cardiac output while also decreasing this parasympathetic vagal nerve as well. So we have an increase in sympathetic nervous drive, and then we have a decrease in parasympathetic nervous system, which is going to cause an increase in heart rate. And again, we're also going to get constriction of blood vessels, which are going to increase pressure. Again, you know all of this. I'm just now introducing these terms to you so we can see how skeletal muscle is going to come to play and basically override this signal. We know that during exercise, we are going to have an increase in heart rate, right? And that's because the muscles just require more goodies. To meet that demand, we are going to have an increase in heart rate, right? So, and I've been kind of saying that is the baroreceptors are going to be responsible for that. And then that means the heart will pump more frequently, resulting in more blood being delivered, right? And this is also controlled by the sympathetic nervous system, right? And you can see here we have sympathetic nervous system is going to increase while the parasympathetic nervous system is going to decrease, right? So it's going to lessen its drive, right? And that will look like this, right? So once the baroreceptors send that message to the neurons, the sympathetic nervous system will fire more frequently, right? We talked about rate of firing, and that just means that it's increasing its activity, which in this case, when we increase that activity, we're going to have more heart rate, more cardiac output. And then it's also going to tell the vagal nerve to decrease its drive, which is acting kind of like a brake, right? And it's acting like a brake in a sense where it's stopping its control over heart rate and letting the sympathetic nervous system take over. So on this slide here, I'm just kind of talking about the exact same thing that I showed you on the previous slide. And again, the vagal nerve works to slow the heart down, right? So when the vagal nerve is succeeding in slowing the heart down, it's firing very rapidly, right? And then as we begin to exercise and the baroreceptors receive the changes in blood pressure, it sends the message to central command, right? Afferently. The brain is going to process it, and the brain is going to say, okay, vagal nerve, stop firing so much. It's going to say, just fire sometimes. See the difference between that fire rate? And that's going to allow the sympathetic nervous system to take over and start firing more frequently. So we get an increase in heart rate, we get an increase in cardiac output, we get an increase in vasoconstriction, and the vagus nerve that is being controlled by the parasympathetic nervous system, it has been shut down temporarily so that the body can keep delivering oxygen and goodies to the skeletal muscle. So I have 2 more slides here, and then this will be over. And again, it's just a review. You guys probably already know this. I just want to prepare you for how the pressor reflex is going to alter this when we get into exercise. So on the next slide here, we are going to look at just kind of a pathway of what occurs. And I have this picture here to kind of show you that. So the cardiovascular response to exercise, of course, as cardiac output is going to increase, and we know why, right? We know that the vagal nerve is being kind of reduced in its activity. We know that the sympathetic nervous system is being increased in its activity. We know that vasoconstriction is occurring. We know that blood pressure is increasing, right? We know that peripheral resistance is increasing, and that just means that we're getting more resistance to blood flow, right? We're getting vasodilation, right? So the blood vessels are also constricting. You know this. You know this all very well, right? And what happens here is you can see that we have a decrease in the parasympathetic nervous system. So that vagal nerve is reduced. That's why there is a little subtraction sign there. We know that the sympathetic nervous system ramps up. This, of course, increases heart rate, and this, of course, increases cardiac output. This is going to also increase stroke volume, right? And that's how this kind of system is working. And then lastly, this is kind of just a brief explanation of how these things all kind of work, and I will let you read that. And then what is going to happen is we are going to get into this section on Monday, looking at muscle-mediated exercise pressor reflex. And we're going to be highlighting what I put here in yellow, looking at how this is going to essentially shut this down and take control over this entire process, or at least take the majority of the control. So we're still trying to understand the pressor reflex, but we're going to talk, sorry about that. We're going to talk about these type 3 and type 4 afferent neurons that exist within the skeletal muscle. And remember, afferent means it's starting from the peripheral and it's going into the central nervous system, or it's moving away from an organ in the peripheral and moving into the central nervous system. So that's all I have for you right now. This was a short one, and we will be back.